Good afternoon and welcome to this conference organized as part of the 10th Montreal Industrial Problem Solving Workshop. I'm Nancy Laramé, IVADO Partnership Director. The Problem Solving Workshop is jointly organized by the Centre de Recherche Mathématique de Montréal and IVADO. It brings together industry representative, academic researcher, graduate students, and postdoctoral fellows. This year, the workshop is 100% virtual and 4 IVADO industrial members participate in the workshop. They are Air Canada, Desjardins, Hydro-Québec, and the International Air Transport Association. In addition to these 4 industrial members, there are also 5 professors who have generously accepted to supervise the 4 teams. They are Philippe Langlais from Université de Montréal, Sébastien Gams from l'UQAM, Yi Yang from McGill, Professor Huang from the United International College, and Denis Larocque from HEC Montréal. Before introducing our guest speaker, I want to mention that we are very pleased that more than 50 students and postdocs coming from 22 different universities have accepted to take up the challenge proposed by our 4 industrial members. These students are located in Quebec, Ontario, Newfoundland and Labrador, Nova Scotia, Alberta, British Columbia, Oregon, California, New York State, France, the UK, and Brazil. In terms of gender diversity, the current student team is very impressive with 37% women participating. I will introduce our distinguished speaker in French, but he will give his conference in English. Please note that this 45-minute presentation will be followed by a Q&A session. To this end, please use the Q&A button for questions you may have. En guise de remerciement pour cet engagement, nous sommes très heureux d'offrir aux participants de l'atelier ainsi qu'au grand public cette conférence du professeur Pascal Poupart de l'Université de Waterloo. Le professeur Poupart possède une feuille de route très impressionnante. Il est présentement professeur en apprentissage automatique à l'Université de Waterloo. Il est aussi titulaire d'une chaire en intelligence artificielle du CIFAR. Et il a aussi fondé RBC Borealis AI Research Lab à Waterloo et est membre fondateur du Waterloo AI Institute. Ses recherches se concentrent sur le développement d'algorithmes pour l'apprentissage automatique avec application au traitement du langage naturel, à l'informatique médicale, à la finance computationnelle, au réseau de télécom et à l'analyse sportive. Le professeur Pascal Poupart est surtout connu pour ses contributions au développement d'algorithmes d'apprentissage par renforcement. Il nous parlera aujourd'hui des récents progrès de l'apprentissage automatique qui permettent des systèmes de plus en plus adaptatifs. Il expliquera également les importantes limitations qui doivent encore être surmontées. Sans plus tarder, j'inviterai le professeur Poupart à venir nous en dire plus à ce sujet.
Merci beaucoup. Thank you very much. All right, so we're going to get started. And then, the question for this talk is, are we experiencing a technological singularity? Okay, so here, here's a brief outline of what I'm going to talk about. So first, I'm going to define what I mean by technological singularity. So this will have to do with artificial intelligence, and in particular, machine learning and ways in which machine learning can lead to self-evolving systems. Now, in terms of this definition and the possibility of a technological singularity, we're going to see that there are some important challenges. And so I've listed on this slide 4 of them. Data efficiency, robustness, open-ended learning, and explainability. Now, in 45 minutes, I don't have time to talk about everything, and there's always a trade-off between, I guess, covering everything and maybe going into more depth about a few things. So I've decided to go into more depth about two of those challenges. So the first one is data efficiency, and I'll tell you a bit about some of the work that my research team has done towards this, in particular, some technique about self-supervised learning. And I'll talk as well about a second challenge, so robustness. So we're going to see that there's some emerging research about combining machine learning and logic that can be quite powerful in that respect. Okay, so let's get started. So first, to motivate things a little bit, let's go back to 1965. So there was a mathematician, his name is Irvin John Good. He actually worked with Alan Turing and eventually became a professor at Virginia Tech after the Second World War. So what he's very well known for is an interesting paper called Speculations Concerning the First Ultra-Intelligent Machines. And in that paper, he essentially described what would be known today as a singularity. So he had already given some thoughts and hypothesized that in some future, there would be some artificial superintelligence, and then it would trigger some runaway technological growth in ways that we would have trouble to imagine and even to cope with. Okay, so this was the first time that people were thinking about this, but then if we go forward a little bit, so in the early 2000s, there's also Ray Kurzweil. He's a computer scientist, inventor, and futurist at Google. And then in his case, he talked a lot about what he called the law of accelerating returns. So what this means is that if we look at this curve here, so we see that human progress keeps accelerating. And the reason for this is that we develop some technology. This technology allows us to go faster, but then to develop the next technology, we can use the previous technology. So at every stage, when we use the previous technology to develop the next one, then we can benefit from the advances that are already possible that allow us to go faster. And that's how these new technologies, they just compound the progress. And then we often end up with a curve that is exponential. And now what's interesting is that when people make predictions about what will happen in the future, often we're at a certain point in time. We look at what happened in the past. So progress was going at a certain rate, and then we just assume that going forward, progress is going to keep going at the same rate. And usually this type of prediction leads to some underestimation, because if the curve is really exponential, or if the progress is accelerating, then that doesn't take into account the fact that the rate would keep on going up. So yeah, this is very interesting. But then there's also a question of, is there a limit to this acceleration? Because at some point, it looks like the curve might just go vertical, or we might not be able to keep up with the progress. I mean, we've all seen how over the years, because of the acceleration of technology, then often it's difficult to keep on adapting. And as humans, we have some limit, right? So is there going to be a point where this curve will essentially stop because the progress will be bounded by our own abilities? And here, this is where Ray Kurzweil essentially suggested that the answer is no, so that the curve would keep on going, and it would not be stopped by any limit that we might have, in part because of what he called the singularity. And here, his hypothesis is that at some point, machine intelligence and human intelligence would merge. So his hypothesis is that there's going to be a symbiosis of technology from machines as well as advances in biology that will lead to some hybrid system. And then at that point, we're going to be able to augment our own intelligence with some artificial intelligence, and then the exponential curve will keep on going. So in 2005, he described this in his book, and he also suggested that the singularity is near. Okay, so now we're in 2020, and there's still a question of whether there is a singularity. Is it coming soon or not? But if we look at our field, computer science, So in the field of computer science, we typically program computers to do every task. So in fact, at universities, bachelor's degrees for computer science are mostly about how to get students to program computers to write code for pretty much every task that we would like the computer to do. Now, there's a new paradigm that started several years ago, but really became popular recently, which is machine learning. And in this new paradigm, we don't program computers directly anymore. Instead, what's possible is that we provide examples to a machine, and then the machine simply learns based on those examples. And so this turned out to be very, very powerful, for instance, in machine translation. So we give examples of sentences in two languages. Also in computer vision, we can give examples of images and then objects that should be recognized. And then the machine will essentially learn how to, I guess, figure out what are the right instructions to follow in order to produce the right output. So this new paradigm is quite interesting because now we don't program directly anymore. We just provide examples. And then based on these examples, machines figure out what are the right instructions. So here, a different hypothesis for the singularity could be that really, in terms of at least a technological singularity, we could define it in terms of self-evolving computer systems. And here machine learning could be a tool towards that. So again, if we don't program directly anymore, then machines are not necessarily limited by our own abilities of figuring out solutions, but instead you see we program at a meta level through machine learning, and then we provide examples and the machine figures out what are the right instructions and then can achieve tasks that we were not capable of programming directly. And then at some of those tasks, in fact, the machine can surpass the accuracy and the performance of humans. Okay, so if we look at the field of machine learning, you could say that, well, historically, most of the successes, at least in the industry, have been based on supervised learning. And here what I mean by supervised learning is this idea that we have some inputs, there's some output that we would like the computer to produce, and then we simply train a predictor, so a computer program, to produce those outputs based on some examples. And here, this is really a static predictor because the machine is trained to simply produce outputs based on certain types of inputs, and that's all it can do. But then there's another type of machine learning known as reinforcement learning, where there's actually a feedback loop. So we've got our computer system here. It takes as input some observations, some data from the environment, and then it outputs some actions that will influence the environment. But then in turn, the environment provides some feedback, again, in terms of inputs to the system, and this keeps on going. So here, with this feedback loop, now there's an opportunity for the system to evolve on its own, to keep on learning, and if, in fact, to achieve certain things that perhaps the original programmer did not necessarily think about initially. So these types of self-evolving systems powered by reinforcement learning are making progress, and some of the applications include games, robotics, autonomous vehicles, operations research, computer networks, also conversational agents, fintech, and many others. Okay, so let me give you now a concrete example of a situation where computers using reinforcement learning were able to eventually surpass humans. So in computer Go, several years ago, DeepMind proposed the program AlphaGo. And this program played Go initially just by supervised learning. So it was trained to imitate human experts. So it was essentially just fed with lots and lots and lots of examples of some board configurations and what an expert would play next. So with this, the machine was able to achieve a certain level of performance, but as you can imagine, if all it does is just mimic what experts are doing, it would not be able to beat humans, right? So it has to come up with some strategies that humans would not think about if it wants to beat them. Now, with reinforcement learning, the machine can also learn by self-play. So it can play against itself, and then it can try different strategies, and then it can eventually figure out some strategies that perhaps are quite different from humans. So it turns out that in 2016, there was this tournament between AlphaGo and Lee Sedol, who was a top human player in Korea. And AlphaGo won the tournament 4-1, so won 4 games and lost 1 game. But what's really interesting is that there was one game in particular, game number 2, where at move 37, AlphaGo decided to position a stone right here. Okay, I'm not a computer Go expert, but for those who are experts at this game, this move should be surprising. In fact, when AlphaGo decided to position a stone at this location, the commentators in the tournament, who were experts, so both in English and Korean, ended up questioning, and they were thinking that perhaps the computer just made a mistake because this was not the type of move that any expert would make. And it turns out that the odds of that move by a human were estimated to be 1 in 10,000. Now, that being said, you can see that Lee Sedol, when he saw this move, he was scratching his head because it's like, well, the computer is not that bad. It should be able to think this through and do something good. And it turned out that this was, in fact, a very good move. And later on, various analysis showed that this move gave a very strong advantage to AlphaGo, and AlphaGo won that game, perhaps in large part because of that move. So here, this was very interesting because it was a case where reinforcement learning made a difference. The computer learned to make a move that humans would not play, and then it won. Now, today, the state of the art is AlphaZero, again by DeepMind, where now there's no more supervised learning. So all the learning is done from scratch by reinforcement learning. Okay, so if we look at perhaps some more industrial problems, so in terms of the evolution of computer networks, various telecom operators are now deploying 5G mobile networks. And in this case, the target is to obtain speeds of roughly 20 gigabytes per second, and the goal is to enable IoT. So this is today, but now if we look at the next few years, so various companies are already working on 6G networks. And what does that mean, 6G networks? So here, it's not well defined yet, but a lot of researchers are talking about how we could have autonomous, adaptive, intelligent systems. The computer networks themselves could perform some form of self-diagnosing, self-managing, and they could also be self-evolving. And in other words, here, these types of networks, it's not anymore about connecting people, but it's more an evolution from connectivity to intelligence. Because once you connect all these devices, all these people, right, then that should enable some more interesting things to take place. And the idea is that now there's a shift happening, even in computer networks, towards some form of artificial intelligence. And then a lot of these ideas, in fact, can be enabled by reinforcement learning. Now, this is not just in computer networks, but if we look at smartphones, there's a similar story where if you look at today's phones, often when you shop for a phone, you would consider the battery life, the camera quality, the screen resolution, the processor speed, the RAM, etc. And then in terms of the software, often you can personalize it by some configuration, and then you also have some voice-enabled command. But tomorrow's smartphones, so various companies are also trying to personalize those phones, but in a way where each phone could adapt by itself to its users. So you could have some teachable conversational and interactive systems. The phone itself could become an adaptive personal assistant, the apps could be self-evolving. And again, a lot of these ideas are gradually becoming possible via reinforcement learning. Okay, let me give one last example. So in Canada, the financial industry is in fact quite important. If we look at financial services, in the past, there was no AI or any machine learning. So what we had was essentially lots of transactions that are essentially, if you want, some kind of a reallocation of assets from A to B. And then the decision to make a transaction was done by a decision maker, right? So a financial analyst or some expert. Now today, a lot of these financial services, the decisions are also enabled by some predictive model. So those predictive models are nothing more than some supervised learning techniques that will learn what might be best in terms of the reallocation from A to B. Now, if we look at the future, so what a lot of the financial industry is currently developing are personalized, adaptive, and self-evolving services. So if we look at questions regarding investments or also making loans, then it's not just to make a prediction about which loan is going to default or not, or which investment is going to be profitable or not, but then the system can get some feedback and essentially learn to improve its prediction over time. And at this point, yeah, we have a self-evolving system. And a lot of those techniques or a lot of these ideas are again enabled by reinforcement learning. Okay, so what I've depicted so far is that the singularity could be happening through these adaptive systems, and machine learning is important for that. But reinforcement learning is sort of like, you know, the at the forefront for machine learning in terms of enabling some really truly adaptive system over time. Now, to achieve this, there's a lot of challenges going ahead. So on this slide, I've got 4 challenges listed. So for anyone who's familiar with reinforcement learning, one big problem is that the current algorithms are quite data inefficient. So we need to improve the efficiency. They're also not very robust, so they're not reliable in various ways. We still have trouble coming up with algorithms that would be really open-ended in terms of their learning. They can usually learn up to a certain extent. They can essentially learn to adapt some parameters, but that has some limit. And often we don't fully understand what those algorithms do, so explainability is still a challenge. Okay, so what I'm going to do for the rest of this talk is I'll talk about some of those challenges. And in particular, I'll talk about first data efficiency. And there's several directions that the community is exploring to improve data efficiency. That includes few-shot learning, meta-learning, transfer learning, multitask learning, and self-supervised learning. But I'm going to focus on the last one. So I'm going to tell you a little bit about some of the work that my team is doing in that respect. With respect to robustness, there too, there's a large community working on improving this. Some of those directions include adversarial training, also doing robust optimization. But then there's another one, which is to combine machine learning with logic in a synergistic way. So I'll explain some of the work that we're doing in that sphere as well. Okay, so now let's look at data efficiency for reinforcement learning. So as a concrete example, if we consider some video games, so here I've got an image of a video game, and we would like a reinforcement learning agent to play this game. So a typical architecture in reinforcement learning would involve a deep neural network that takes as input the image, and then it decides which action to execute in the game. And after executing them, it gets some rewards. These are points essentially in the game. Now, the problem is that even though this works well, it does take a long time to train those reinforcement learning agents. In fact, it might take on the order of millions or tens of millions of interactions with the environment. So in contrast, humans can learn to play those games much faster. So in many industrial applications, in fact, that's a bottleneck. So we'd like to reduce the amount of data that is needed to obtain some good performance. Okay, so one idea for this that my group has explored, as well as many other groups, is what is known as self-supervised reinforcement learning. So here, the main difference is that instead of training our deep neural network just based on some rewards that might be sparse, here the rewards would be essentially points that are given perhaps at every turn or simply at the end of the game. And here, if our deep neural network has 1,000,000 parameters, then and at every time step it receives a reward or perhaps even no reward, so that's why I'm calling this a sparse reward, then it does often take millions of time steps before those millions of parameters get trained. So if we want to train faster, one idea is that we need to have a more, well, a richer signal. So one possibility is that we could get the network to essentially predict the next image. So if you're playing a video game and you're going to come up with a good strategy to play this game, then you better have an idea of what is going to happen next as a result of your action. And if you can predict what will happen in this way, then there's a good chance that you'll be able to come up with a good strategy. So here, if we train a network to simply predict what the next image is, the next image consists of millions of pixel intensities, so that's a dense signal, and it can learn way faster with this. So I'm going to show you how, in fact, we did that and obtained good policies much faster. Okay, another problem when we compare humans to machines for playing video games is how information is treated. So if you look at this game, this is a classic Atari game known as Sequest. And if it's the first time you see it, you actually, without knowing how to play this game necessarily well, you can guess what this is all about. So we've got a little submarine, it's shooting some enemies, and you can get a feel for what you might want to do based on that. And so a big difference between humans and the machine is that humans essentially see moving objects in the game immediately and start thinking about a strategy based on that. In contrast, reinforcement learning agents, they receive a matrix, or otherwise an array of pixel intensities, and it's not clear for the machine how to interpret that. Okay, so that's a big difference, and that explains also why it takes such a long time for the machine to eventually figure out good actions. So what the machine really has to do is, with this deep neural network, it has a part of it that essentially does feature extraction to interpret what those pixel intensities really refer to, and then there's a part as well that does the policy optimization. So the network is really responsible for those two parts, but then it turns out that the feature extraction part is the part that takes a really long time to figure out, and that's why humans have an edge. Okay, so now an interesting question is, could we get a machine to learn to segment the moving objects automatically and then be at the same level as humans in terms of playing, in the sense that we'd be able to play directly based on objects as opposed to just pixel intensities? So it turns out, if we look at the literature on computer vision, there's been a lot of work on estimating motion, estimating structure from motion. So if we are trying to identify different objects here, like cars, people, and so on, based on a static image, then it's often labor intensive to manually label every pixel here. But if, on the other hand, we have a video sequence, and then in that video sequence we have objects that are moving, like a cyclist going forward, some pedestrians that are walking, then we can measure the optical flow of those pixels, and that already gives us a sense of what objects might be present, because here there's a hypothesis that pixels that are moving similarly must be part of the same object. Okay, so this is something well known in computer vision, but that's something we can exploit to essentially learn to recognize objects automatically without any need for labeling or supervision. So several years ago, there was a network proposed by Google called Structure from Motion Network. What we did is we adapted it to video games. We essentially simplified it to be just in 2D. And then our network works as follows. So we take as input two images that are adjacent in the video sequence. Then we have some convolutional layers that extract some information. And then the goal of all of these components will be to estimate the optical flow of every pixel. And then based on that, now if we take the first image plus the optical flow, we should be able to reconstruct the second image. And if it's not accurately reconstructed, then we can backpropagate the error and train all the components here. But then in those components, we also estimate object location via some masks and also object motion in the form of translation and camera motion in the form of translation. So the idea is that you see the optical flow can be obtained by estimating where the objects are, what their motion is. Now, if you add this to the first image, you should be able to reconstruct the second image, and any error can be backpropagated through the entire network to update all the parameters. And here you see there's no need for labeling anything, right? So we just need a sequence of images. So we did that and applied this to various video games from the Atari suite. So here, just as an illustration, I'm taking two games, Breakout and Pong. There's two frames, frame 1, frame 2. So in this game for a Breakout, we've got a paddle, we're hitting the ball, and the ball has to essentially destroy the ceiling gradually. So the moving objects here are really the paddle and the ball. So what our technique does is that it computes some object masks that essentially segment those objects. So here it recognizes the ball as well as the paddle. And then it also recognizes their motion. So this is an illustration of what the network can do. You'll notice that the segmentation is far from perfect, but the goal here, in fact, is not to do segmentation per se, but just to extract information about object location and motion. And you can see that it does a reasonable job in that respect. So then we combine this network with a more classic reinforcement learning architecture. So I've got here the network that I just explained that computes optical flow. And then I've got a bottom part that is the more classic architecture for reinforcement learning, where we'd have various convolutional layers that eventually feed into an actor network and a critique network. And here, this part would normally work directly from the raw pixel, but what we do is we augment this information with the object level information that comes from our segmentation network at the top. So here, this network has some masks that essentially corresponds to the segmentation, as well as some translation that tells us the motion, and we feed that as well to the network for reinforcement learning, where the actor essentially selects the action in the game. So when we did that, and we compared that with some techniques that are classic benchmarks like A2C and PPO, we were able to improve the speed at which we could get some good performance for 26 games. And it was roughly similar for 30 games, but worse for 3 games. And compared to PPO, we improved for 25, got similar results for 25, and worse for 9 games. So now let me illustrate those results. So we've got here videos for the 4 games that I've been talking about. On the left side, this is the normal view when you play as a human. And on the right side, we see the object masks in real time that are recognized by the machine. So you can see that the machine is tracking quite well the paddles and the ball. And in general, you see it tracks well the moving objects in pretty much all the games. So for those games, the results were generally good, except for this game in the bottom right here, Beam Rider. So you'll notice that for this game, what happens is that we have some beams, which are those blue lines, that essentially just floating down the screen, but they're completely irrelevant for the game. So what matters are, in fact, those enemies and the bullets that they shoot, but they're so small compared to the beams that they don't get detected. And this is an example where performance is not improved because of that. So in fact, you see the object level information of the beams is just creating some noise that doesn't help the reinforcement learning agent. Okay, so in terms of performance, we can see on those 4 games how our technique did. So our technique is the one in yellow. And here, the idea is that we want to earn as much reward as possible, as quickly as possible. Okay, so a curve should be as high and as left as possible. So our technique, which we call morale, is in yellow, so it did well on those 3 games. And then, as I explained for Beam Rider, it was not able to get any edge simply because the information from those moving objects was irrelevant. Okay, so this was the part about data efficiency that I wanted to illustrate, that shows how we can improve simply based on self-supervised learning using some techniques from computer vision, but otherwise techniques that allow us to work at the object level. Now, another big problem for machine learning is robustness. So now for the rest of this talk, I'm going to talk about the second problem. And here, when we talk about robustness, there's typically 2 types of issues that are usually referred as robustness, or at least lack of robustness. So there's the notion of adversarial examples. So if you have an image like this one, which is a panda, and the machine is able to recognize that this is a panda, but now you add some noise. So the noise is just varying the pixel intensities, and in a way that doesn't really change how the image looks like. But then for the computer, it will be sensitive to this noise, and it might recognize this as a gibbon. So this is a problem. Another problem is that all those techniques for machine learning, or at least the vast majority of them, use some form of optimization. The optimization is typically non-convex, which means that it might get stuck into local optima instead of finding the global optima. So that means we're not finding solutions that are as good as we had hoped for, and those solutions might be arbitrarily bad. So I'm going to focus on the second problem here and explain how we can combine some techniques from machine learning with some techniques from logic to essentially obtain solutions that will find the global optimum faster than otherwise. Okay, so to illustrate this work, let's talk about Boolean satisfiability, which is really a foundational problem in computer science. So this problem is the one where we're trying to find an assignment of Boolean variables that satisfies a set of clauses. So I've got an example here where I've got 2 variables, in fact, 5 variables that are in different clauses. I'd like to make all those clauses true. And it turns out that in this case, there is a satisfying assignment that sets v1 to true, v2 to false, etc. Now, this problem is foundational because it's an example of an NP-complete problem. Okay, so the current state of the art for satisfiability is to use solvers that are known as conflict-driven clause learning. So conflict-driven clause learning corresponds to this architecture here, where we have a set instance. This set instance, we're going to try to assign some variables, and at every step, we essentially gradually construct a search tree where those variables, we have to choose which one to branch on next. And let's say we arrive at a point where it's impossible to satisfy the instance, then we would find a conflict, and we would backtrack and then try a different assignment for some variable, like this one here might be changed to false. So the idea is to find conflicts and then to change our assignment accordingly. But each time we find a conflict, then we can add a clause, and that's where the clause learning takes place, and that tends to help afterwards to find a solution faster. Okay. Now, in these types of techniques, there is one box that is very important, is a box here that decides which variable to branch on. So what I'm going to do next is explain some techniques for essentially learning how to branch. Okay, so one way of viewing branching heuristics is that they are selecting variables to branch on that will lead to conflicts as quickly as possible, so that we're learning as quickly as possible. And here, if we want to speed up the learning, and here it's essentially to find conflicts, then we would like to select variables that will have what is known as a high learning rate. And here the learning rate can be represented simply by the ratio of the learned clauses that involve that variable divided by the total number of clauses that have been learned. So we'd like to select variables like this that have the highest learning rate possible. And then so one way to model this is through a multi-arm bandit problem. So that's a simplified version of reinforcement learning. And one heuristic for this is to select the variable with the highest exponential moving average of this learning rate. Okay, so this is the formula that we're using here. So this is a completely adaptive technique. And I've got a slide here that shows the results. So back in 2016, when we developed this, we compared that to different branching heuristics that were either not adaptive or even completely handcrafted. And our technique LRB ended up performing the best here. These are cactus plots where we'd like to solve as many instances as possible in as less time as possible. So essentially we want a curve that is on the right and as low as possible. So in 2016, we won a gold medal for the best SAT solver in the competition. And then in 2017, a silver medal, just based on this idea. Now, this is just using learning in the context of one aspect of those SAT solvers. But an interesting question is, could we actually do SAT solving with the full machine learning package? And it turns out that yes, we can formulate satisfiability as a machine learning problem, and that leads to some new ideas for doing satisfiability. So okay, here's one way of formulating this as a machine learning problem. So we have some variables that we don't know whether we should set them to true or false. So we're going to denote by theta the probability that the variable should be true. So if I have 5 variables, then I'm going to have 5 thetas here that represent the probabilities of each variable being true. Now, based on that, based on those thetas, we can compute the likelihood that a clause will be true. So yeah, here I've got the formula that shows that if a clause says that V1 should be true, or V2 true, or V3 should be false, then the probability that the clause will be true will be equal to this, this formula here. Okay, and it corresponds to this graph here. So with this formulation, it turns out we can formulate satisfiability as a Bayesian learning problem, where we start with a prior. So I'm going to have a distribution over my theta parameters. Here I'm going to use a product of betas. Then I can compute by Bayesian learning a posterior, which is the multiplication of the prior by the likelihood and renormalizing. When I do this, I obtain an exponentially large mixture of beta products. And here, the idea is that because it's an NP-hard problem, right, then naturally there should be an exponential complexity in the computation, and that corresponds to the fact that these mixtures of beta products in a posterior, there's going to be exponentially many of them. So this is normal. Now, we'd like to have an algorithm that is tractable, so we proposed an approximation known as Bayesian moment matching. So the idea is that at every step, we'd prefer to have a single beta product for the posterior instead of a mixture of beta product. So let's say we start with a single beta product, then when we do our Bayesian update, which corresponds to taking into account one clause, then we'll obtain a mixture of beta product, but then at that point, we project this back into a single beta product by matching the moments of the distribution. Here, matching moments simply means to match the mean and the variance. So these would be examples of some moments of a distribution. So it's an approximation, but it allows us to gain tractability. So here, what I've described is essentially that we can formulate the satisfiability problem as a machine learning problem. And in fact, if we do exact Bayesian learning, we could solve SAT problems optimally. The problem is that it's not tractable. If we do an approximation using the Bayesian moment matching technique that I explained, then we give up on optimality, but then we get an algorithm that is tractable. So ideally, we would like the best of both worlds. Now, naturally, achieving the best of both worlds would suggest that we could show that P equals NP, which is unlikely. But nevertheless, there might still be some ways of combining these ideas to obtain, well, to improve the state of the art. So it turns out that with the Bayesian moment matching approximation here, we can often satisfy 99% of the clauses in less than 1 second. So this is very fast. But then we still don't have optimality, but we can achieve optimality by combining that with a traditional CDCL solver that is exhaustive. So when we did that, so the idea is that we can initialize the solution based on what the Bayesian moment matching technique suggests. And then after that, we let the CDCL solver do a search and find a solution. So we tried that on several benchmarks, in particular on what are known as hard cryptographic benchmarks. We can see that when we initialize with Bayesian moment matching, then we improve the results. So here we've got 3 types of solvers, one called MapleSat, another one Glucose, another one CryptoMiniSat. For each one of them, we've got a version with and without Bayesian moment matching, and then the version that is with Bayesian moment matching works better. Okay. We also tested this on the SAT 2018 benchmarks using a state-of-the-art solver called MapleComps-PS. And there too, we obtained state-of-the-art results. We improved the state-of-the-art. So in general, so what this shows is that by combining the two, we can improve efficiency and retain optimality as well. Okay, so let me conclude now. What I talked about today is essentially this idea of singularity that we could define in terms of self-evolving systems. We saw that with the logs of accelerating returns, then there's often exponential growth. Now, with technology, we can see that machine learning is essentially allowing us to leverage that because we are now essentially doing some meta programming. So we're writing computer programs that write instructions essentially for solving other tasks. And then that has enabled a lot of advances. We talked about several challenges, but I talked about 2 of them in particular, data efficiency and robustness. And I explained some techniques for making progress in terms of resolving those challenges. So we can use self-supervised learning. And here's the paper if you're interested in reading more about what I presented. And I also talked about I guess, combining machine learning and logic in a synergistic way. These are the 2 papers that describe the work that I explained as well today. So now this is really just what my group is doing. There's a large community in Montreal and elsewhere that are advancing the state-of-the-art of machine learning, reinforcement learning, and so on. And there will continue to be advances. Now, coming back to the question of, is there a singularity? I don't know, but there's one thing that is sure is that we're going to continue to have systems that are gradually more adaptive and more autonomous. Okay, so let me stop here and I'll be happy to take some questions.
Thank you, Professor Poupart. So if anybody has questions, so feel free to ask your questions through the Q&A buttons, and then we'll be able to read them to Professor Poupart. On my side, I may have one question for you, Professor Poupart. If I understood well, when this technical singularity is mostly linked to the increasing capacity of machines to learn from data, and how will this be related? I know to the increased power in computation power for the computers.
Yeah, so it's definitely all related. So I guess the increase in power has been very important for machine learning. In fact, some of the techniques for deep learning that we're now really enjoying in the last 5 years or so were proposed by Jeff Hinton's group already back in the late 1980s. But at the time, they just didn't have computers that were as powerful, and then they just couldn't demonstrate what we're seeing today. So now if we go forward, right, we can see that, for instance, in natural language processing, there are these very large transformers, and the current systems that we have are still limiting what we can do. So with more computational power, more data, transformers have improved the state of the art in natural language processing. And each time a group essentially tries with more data and more computational power, then they gain some advantage. So there's evidence that this matters a lot, and it should continue to help going forward.
So I think we received one question from Dorian from AIR. Data efficiency. What are your thoughts? What are thoughts on advances that use a human to provide either example or influence the reward to accelerate learning?
Yes. Okay. This is a great question. So indeed, if we can have a hybrid system where the reinforcement learning agent can essentially ask for help from a human expert, then that reduces the amount of exploration. And it's a bit like, you see, when you're working with an expert, then you can make fewer mistakes, and then you can obtain an overall better system. So in terms of data efficiency, then the ability to query an expert will definitely help to reduce that. Now that brings in other challenges though, because often the problem is that experts don't like to be bothered too often by computer systems that don't know what they're doing yet. So here there's a trade-off, or at least there's a balance that has to be achieved, where you'd like the system to essentially ask the expert, only when appropriate, and then but I do believe that there's a sweet spot for this.
Thank you. So we have other questions coming in. So for example, yeah, so there will be some potential industrial applications for these technologies. So, and how long do you think it will take to reach broad industrial application for these technologies?
So, well, some of these algorithms that I described are used by various companies. So I know that, for instance, in finance, reinforcement learning is used, and is used for automated trading. So that is happening already. I know in computer networks, there are various companies that are gradually inserting different machine learning techniques, either supervised or reinforcement learning technique, to essentially make their systems more adaptive. So at the moment, often the systems have to be configured by hand, and each time there's a change, then somebody has to change the parameters by hand and so on. So the maintenance costs are quite high, but then these things are gradually being replaced as we speak. So that is being, this is happening now. So yeah, there's, I guess the number of examples might still be small, and those examples might not always be highly advertised by the companies, but they are gradually increasing.
Thank you.
There's one participant that would like to have some suggestion in regards to nice book that explain reinforcement learning.
Oh, okay. Yes, well, okay, so by far the most important textbook would be the one by Sutton and Bartow. They released a new edition, I believe, just a year or two ago. Now, the field of reinforcement learning is progressing very, very, very fast. And I would say that the book doesn't do full justice of the state of the art at all. So at the moment, in fact, there isn't, I guess, an up-to-date book. And in fact, that would probably be impossible because every month, every year, there's new advances, and it does take time to write a book. So, so what I would recommend instead is to simply go online and watch various tutorials on YouTube. And if anyone's interested, in fact, I just taught a course online this summer, CS 885, and then all the video lectures are recorded, and it's all available there. And I'm not focusing on a single textbook. So in fact, I take material from different sources in order to obtain a course that is reflecting the state of the art.
So we have a question about machine learning interpretability. So what, in your opinion, would be good approaches to help in improving the interpretability of machine learning?
Okay, yeah, that's a tough question. So there's there's an entire community that is working on this. So it varies depending on the technique. So some ideas that have been explored for improving interpretability are to use what are known as probing techniques. So if you've got a neural network and you're not sure what information this neural network is really containing, and what is it really using in making its predictions, so you can use probing techniques to essentially probe what is in the different neurons. Those probing techniques essentially amount to designing another predictor, and then if that predictor can predict some information, then it means that this neuron that this predictor was using as input contains that information. So I guess what happens is that neural networks are uninterpretable, generally speaking, but you can often augment them with these probing techniques that then can reveal what information might be present. So this is one way to achieve that for any type of neural network. Beyond that, there are ways as well of structuring the neural network where if you have the right type of computational graph, then you'll be able to interpret. So a bit like what I presented with respect to the segmentation network. So here we understand already how images are generated based on light and so on, and how objects move based on physics. So the network was structured in a way where we knew for sure that the object mask did capture the location of the objects. So often, if you structure your network in a very careful way, it might be possible to constrain it in a way where the network will have no choice but just to compute the things that you care about, and they will therefore be interpretable. So that's another approach. But I'm sure that there's many other ways as well of approaching that.
Okay, one participant is asking a question for his child. So as you mentioned earlier, computer science, we program computer to do some tasks. Machine learning, we show computer example to train and learn. What will the future student of computer sciences be doing in 10 years or 15 years' time?
Okay.
Asking for my child.
Yes, yeah, great question. So, well, I guess at the end of the day, we will probably move towards some sort of hybrid approach where right now, most of the programming languages are about how to write down instructions, right? And if you want to do machine learning, I guess you write some programs that take as input the examples. But now, what I speculate is that there will be new programming languages in the future that will integrate machine learning as some primitive instructions directly in the language. So with that possibility, then we're essentially going to be describing at a higher level some tasks where those tasks we're also going to say, well, in order to perform well on that task, you need these types of examples, and then the machine will essentially figure out how to use that. So you could think of, computer programmers essentially becoming more like managers of those machines, where you essentially give higher level instructions, where those instructions are not necessarily depicting precisely the steps of a solution, but more like, the general ideas and what type of data you need, right? So that's what I think is going to happen. I mean, we're still going to need people to program computers, but perhaps the languages, the type of instructions, and so on will be different, and will most likely integrate different forms of machine learning for this. And in that respect, there's some recent work from OpenAI. There's a system called GPT-3 that they're releasing as we speak. And it does what is known as few-shot learning, where you specify a few examples, and then it can then infer what to do based on that. So here, this is beautiful because people don't have to be experts in the details of how to program computers, but then they also don't need to have very large data sets. They just need to provide a few examples, just like when you teach a child, you would demonstrate how to cook a recipe or how to perform a task, just a few times, and then the child would figure out what to do after that, right? So that's something that is emerging as we speak, and I believe that in the next 10 years, this will become more and more important.
Well, so we have another question related more to, I think, autonomous vehicles. So it's, related to situations where, for example, reinforcement learning algorithms and models won't be able to experience, for example, how to learn not to drive on pedestrians while not being allowed to experiment it.
Okay, I didn't fully understand your question. So you said the algorithms will not be able to learn from.
Yes.
Okay, wait. Okay,
where situations where the algorithm will be confronted to the real world problems. So, for example, how to learn not to drive on pedestrians while the model is not being allowed to experiment, for example.
Okay. Yes. Right. So, okay, in the field of autonomous driving, there's a lot of simulators that people use. And in fact, you could say this is similar to, when it comes to driving a car, before we drive for the first time in our lives, we sit in a car for many years as children, then teenagers, before we actually start driving. So we've actually already experienced and seen demonstrations by our parents and other adults how to drive, right? So then we can learn a lot from that, and there's a whole field of learning from demonstrations that essentially tries to teach machines also to learn from human drivers. So that's one approach. Another one is to use a simulator. So if you want to experience what it would be like, I guess, to have a collision, drive on pedestrians, but without the consequences, right? Then you can try this in simulation and learn from that experience. And we could say that even humans do that, right? So pilots for aviation would learn in simulators. So that's something else as well that is done. Yeah, so I would say these are some of the directions that at least are being explored by the community on autonomous driving.
Okay, thank you. Maybe we can take a last question, because I think we are almost running out of time. So
one participant is kind of asking a question that regards humans losing control. Do you have any thoughts on the fact that there could be a dark side to singularity?
Yes. Okay. Well, so yeah, that's definitely something we should be concerned about. So if we achieve the type of singularity that I described, where we have these self-evolving systems that essentially are doing things that the programmer had not thought about in the first place, then there's a risk indeed that we're going to lose control. The computer is going to do some things that might have some bad consequences. But at some level, you could say, well, that's no different than when parents teach their children, right? When they become teenagers, at some point they start doing things that their parents never thought they would do. And then at the end of the day, you know, you raise your children to become good people, but you know, and anything can happen. So I guess with computer systems, there's also the field of, I guess it's, well, the field of verification, where you design a computer system, but then you want to verify that it will perform according to some metrics at a certain level. And, and then there are ways in which you could have one computer system that, okay, is self-evolving, but then there's another computer system that its job is essentially to monitor how the first one is doing and to keep it in check, right? So there are various techniques that one could use to essentially try to keep on monitoring and verifying. But I must say that this will never be perfect. And yes, there is a chance that some bad things will happen as a result of that.
okay, so okay, maybe do we have time for a last question, or?
Yeah,
okay, so
I guess I can take one more if you want.
Okay, so we have so one last question. So about robustness. So regarding the theme of machine learning and logic to solve robustness. So what are your thoughts on the neurosymbolic AI and the key areas of progress there?
Yes, so absolutely. So neurosymbolic AI, well, I guess what I explained about machine learning and logic can be thought in terms of neurosymbolic AI. So here the neural part is really the machine learning part. The symbolic part is really the logic part. And here I think that there's plenty of directions to be explored. I don't have personally some specific directions to suggest, but on the other hand, I think that this is definitely something very promising that will bring, I guess, lots of progress. So yeah, and here, yeah, it's not something that is well established yet. So there's a lot of people starting to look into this, and it's bringing together fields that were often considered separate, but then they're complementary. So that's why we can often obtain some hybrid approaches that have like the benefits of both worlds. But yeah, I would say here, you know, just to go and explore and try some things.
Thank you.
Okay, I think that that's the end of our webinar. The webinar is going to be on our YouTube channel. So if you have colleagues or people you know that would like to to watch it again. It's gonna be on the Ivado YouTube channel. So thank you again for your participation, Professor Poupart. I think that just by the number of questions we receive, we got great interest from all participants. It was probably your vacation period, so I really want to thank you even more. And thank you to all people who attended. At one point, we had over 100 participants online. So I think this is a great webinar, and I want to thank everybody that took time to attend to this webinar. And thank you again for your participation, Professor Poupart. This is really appreciated.
Well, thank you as well. So it was my pleasure, and this sounds like a great forum and a great workshop.